We are discussing about this decision tree algorithm, and in fact, in the last class, I discussed also some of the issues regarding overfitting of a decision tree classifier, and then some of the methods to handle that. And in particular, we discussed with respect to this algorithm ID3. So today, let me give you a bit summary of this algorithm. So as you see that in this algorithm, the input would be your training examples, which means that here you have the, for each training example, you have the set of attributes, and also you will have the target attribute. And particularly, we will discuss with respect to two-class classification problem. So we consider there are two types of attributes, positive and negative, and this can be extended even for multi-class classification. Now the process is that we create a root node, and then we check the distribution in the training examples. If you find a very trivial case that all examples are positive or all examples are negative, so accordingly, we can label that node either by positive or negative. And also there may be that no, you do not have any attribute set there in your set, it is empty. Actually, it's a recursive algorithm, so that's why this step is required. You will understand when we describe the other steps. So then you have to label that node with the most frequent level. So which means that you should consider the overall, just before that, whatever training examples were there, you find out what is the most frequent level that you should consider. It's a kind of missing value scenario. We'll discuss this part also later on. Otherwise, what you need to do that you have to select the best attribute. We discussed the procedures of selecting best attribute in the previous class. That is the information gain out of possible set of attributes. You find out that attribute which provides you the most information gain, and you should select that. And then you consider branching over the values, possible values of these attributes. So if you consider the attribute value, we are considering here the attributes are all having discrete values. So you have, and also that's a finite number of values there. So you have a finite number of branches depending upon a particular, depending upon a value. So if a value is vi, for example, of a, find out all the subset of training examples, what you are handling presently at that node, find out that subset which has this value of a is vi. So here is the question that suppose this vi is not there. So what do you do in that case? Because in your unseen instance, it may happen that at that node, you get an instance with the value vi at that positions. There, if S is empty, what you should do that you should return by adding a leaf node below with the most frequent level. Okay, and in fact that is what was there also in the trivial case. And otherwise, what you should do that you should recursively call this particular algorithm ID3 with S to form the subtree. So this is a recursive call. I hope this is understood. You have already gone through. I know that. Just to summarize, is there any doubt regarding this algorithm? In fact, this is the algorithm you are mostly implementing in your assignment. So any question? Okay, so let me proceed in that case. You see that actually what you are doing here, you are conducting a search for hypothesis, and in that hypothesis space, and in hypothesis space you have all possible tree structure of a decision tree structure, and which is representing in fact a target function, all possible target functions in the as a form of Boolean expression. We have discussed that how decision tree is equivalent to a target function in the Boolean form. And our goal was to find the best decision tree, but naturally this search is not exhaustive. As you can see, it's a kind of greedy search, because you followed certain principle while doing that thing, that information gain you are considering while splitting, while considering the choosing an attribute and going for branching from there. So you will get a particular hypothesis, but to get the decision tree which is meeting this criteria of Occam's razor's principle, that your hypothesis should be as simple as possible, which means the size of the tree should be minimal. That kind of problem is NP-hard, and but we are performing a greedy heuristic search. And we are these slides I discussed in the previous class, but I'm just simply going through once again. So this is the ID3 algorithm's characteristics once again. That first thing is that hypothesis space is complete, which means that your target function in that form will be there. Always your target function is included into that hypothesis space. So that is the part. And also, as you have seen, that it's a you are trying to locally optimize the gain, locally optimize the gain. Using the gain, you are trying to locally optimize the performance or the size of the decision tree, I should say. It's a kind of size versus accuracy. So there is no single optimization functions we are using. It is not really we are evaluating some optimization functions. It's a kind of heuristics we are applying with the hope that you are going to get some kind of trade-off between your accuracy would be, say, consistent. So in this case, no, it is possible to get consistent. So which means the training, with respect to training example, your training error could be 0. So if you consider training error is your objective function, so it would be 0. But what is the criteria is that you are trying to keep your size is minimal. So in that case, it is the size of the decision tree, which is the, say, number of nodes. That could be one measure of the size, and the other kind of size could be it is related to the depth of the tree. So we are trying to keep them as small as possible. And yeah.
Hello, sir.
Yeah.
Hello.
Yes.
Sir, can you please explain another times backtracking? What is about backtracking, sir?
Backtracking means at any point if you find so when you are throwing out certain attributes at certain decision, suppose you are choosing the best attribute at a particular node, okay, and you are going on till expanding the tree. At certain point, you felt that somehow your performance, your accuracy is not going to. There is some kind of observation that your tree is really going deeper and deeper. So you try to look at back. You go back to those nodes where you have chosen the attribute A as the best. You can choose the next possible attribute which is in the ranking, and then again try expanding from there and try to see whether that gives you better tree topology, a minimal tree topology. I mean, that gives you a smaller tree topology. So that is the principle of, but you are not doing it here, right? You are really taking a decision, and that's the final decision at that node. And finally, whatever tree you are getting at the leaf nodes, so whenever you form the leaf nodes, you are getting the result. So that is the implication. Is it clear?
Yes, sir.
Okay. So these are the things we discussed, and as I say, no backtracking. And statistics-based search choices, we understand that. So we are using the distribution, class distribution over the training examples at your hand at that node. And depending upon the measure of entropy over that distributions, you are choosing the attribute. That is the kind of criteria we have applied. And this is also applicable for noisy data also. So which means that even if you don't get a consistent hypothesis, still it works. And you will get so of course certain error, training error, but the generalization error may be better than getting a consistent hypothesis with that examples, if there is a noise. So this part also we considered in the previous class, that there are two kinds of bias that you can observe if you compare this decision tree based technique with respect to the concept learning technique. One is that restriction bias, where the hypothesis space itself is constricted. That means you are not taking the complete hypothesis space. Your hypothesis, your hypothesis structure is such that there is a certain subset of hypothesis space which you are allowing as the form of a target function. Now, your target function in reality may not be in that form, but you are assuming that there is a particular type of form, a bias in that form of a target function, and that puts a restriction on the kind of set of hypotheses on which you will be looking at. It's the language bias analogy. I mentioned that you can have all possible combination of words in a language. If you say, yeah. Is there any question? There is someone's microphone is not muted. I would request please mute your microphone. If you are not muted, please mute your microphone because that background noise is coming. Sudipto, Sudipto, can you see that someone's microphone?
Yes, sir.
I think it is
Shubhra Shankar Chatterjee.
Hello.
Yeah, please mute your microphone.
Hello.
Subhra Shankar Chatterjee, please mute your microphone.
Sir, even you can also mute.
Yeah, I'm just checking. Actually, I don't want to do that thing. It just interrupts. Let me get that one. Oh, okay, so thanks, Shubhra. And he has already muted. So, that is what I was mentioning, that you can have this kind of language bias, or you can have preference or search bias. That means you are considering certain criteria based on which you are choosing, given a set of candidate hypotheses, you are selecting one of them, giving preference to one of them based on certain criteria. That's what you are following in the decision tree. So here, of course, your search is not exhaustive. But as you can see that you can handle a larger hypothesis space in that case, because if you are going to use the restriction bias, if you keep your hypothesis space small, then you can consider some kind of exhaustive strategy, though you are not always taking exhaustive strategy, but there you can handle in a better way, because your hypothesis space is usually smaller. Better in the sense that you can consider all possible consistent hypotheses, like what candidate elimination algorithm is providing you. But the restriction is that target function may not be there in your version space. But in your decision tree kind of algorithm like ID3, it has a preference bias. So target function is surely going to be included in your version space. And if you are going to get a consistent hypothesis, and from that, so that target function will be one of the consistent hypotheses if you assume that there is no training error, if you assume that.
Sir, can you explain once again how this language bias creates incomplete hypothesis space and
the search bias preferences creates incomplete search strategy.
Yeah, I mean, have you understood the concept learning part with candidate elimination algorithm?
Yes, sir.
So in that,
I understand.
yeah, in that concept learning, what kind of form of hypothesis we have considered?
Conjunctive.
Like in IIT algorithm, we are conjunctive all the paths to the leaf, and there this and the or of all the paths like that.
That is, you have not answered my question. My question was that what was the form of hypothesis which you have considered for this candidate elimination algorithm when you learned this concept learning?
This conjunction, sir.
It's a conjunctive form, right? So as you see that your target function may not be always in that conjunctive form or conjunctive normal form. Just now you mentioned, no? So
Yes,
that
sir,
is
yes,
the but your hypothesis space is only conjunctive normal form. So that is the incompleteness. So you're not considering the whole hypothesis space of the Boolean expressions. Is it clear?
sir. Yes, sir. Yes, sir.
So that is a restriction bias, because the restriction bias is that you have restricted the form of hypothesis. It has to be in the conjunctive normal form. You are not allowing any disjunctions. If you allow disjunctions with conjunctive normal form, then it becomes a very general Boolean expression, and then no, any target function in the form of a Boolean expression can be accommodated. Okay, so so that is the kind of restriction there. Whereas if you have a target function, I mean, if you have the hypothesis in a more general form, like decision tree, as you just mentioned, disjunctions of conjunctive normal form. There you have all possible hypotheses. You are allowing all possible form of hypothesis for, for formation of hypothesis, all possible structures. Fine? Is it clear?
Yes, sir.
So then the question is that now which hypothesis you are going to consider which will fit the best training examples, and also it should keep your generalization error low. That is the question. So it's a search. As such, the problem is a search problem. You have a hypothesis space and you are trying to find out the best hypothesis as per your criteria. Is it clear?
Yes, sir.
So this search, as you can see, that since your hypothesis space is so large, no, you cannot completely look at all possible things. Like it's not I'm saying that you have to always exhaustively search hypothesis space. I'm talking about even all possible candidate solutions with respect to training example, that also you are not going to check. What you have done in candidate elimination algorithm because of the smaller size of hypothesis space. Right? So there you are giving preferences rather even from that set also. So in your version space, you are giving certain preferences to some of the consistent hypotheses, something like that. So Vijit, have you understood?
Yes, sir.
Okay, so let me then proceed. And so what are the inductive bias in ID3? As you can see that our preference is for short trees, and we are considering, we are assuming, that's also a kind of assumption, that high information gain attributes near the root, that means nearer the closer to the root, they will give you a shorter size of the tree. That's a kind of good heuristics, because the as you see that it is coming from that information theoretic understanding, that is lower the entropy of a set, higher, better is its structure. I mean, you can say that it has, it requires smaller, I should say, rather smaller encoding to represent that structure, right? Smaller. So that is a kind of interpretation of an entropy. If you have entropy, higher entropy for any kind of distribution, which means the elements to represent that element of that distribution, you require higher number of bits, higher number of, you require a higher number of, higher size. So this concept, this heuristics is applied while applying this information gain. If you have higher information gain, which means you are going to achieve higher reduction or higher reduction of the requirement of your size of your decision tree. So this principle also is driven by a general scientific hypothesis, general assumptions in the science that is called Occam's razor, which means that you are going for, you will preferring simpler explanation, or in this case, the shortest hypothesis that fits the data. So the justification is also, you can look at this, you can consider this justification that if you have a short hypothesis, which means you are trying to say that there is some kind of less chance factor to that kind of hypothesis. It's a kind of say, if I say, for example, just looking at one example, if I say if this satisfies, then this happens. Actually, there is a fact, there was a fact which was true with respect to that, because from that you are drawing this example. But whether it is a coincidence, just it has happened. It's just by chance, because there are other hidden variables, other different causes. That is not very, you are not ensuring that. I mean, so if you consider all possible conditions, you do not know exactly which are mostly responsible and which are not really relevant. But still, in your observation set, just because they are there, you are trying to say, okay, no, that has to be satisfied. You are trying to ensure that. So that is the, I mean, condition. So you have, sorry, I have to take water. So if you consider the probability of occurrences of every factor, every conditions, probability of satisfying every conditions, and joint distributions of those conditions, you will have a smaller probability because of that. We'll discuss with respect to probabilistic interpretations later on also. So the smaller this size, better is the likelihood of fitting the data, and whose probability is higher, I should say. Likelihood is that higher, with higher probability of fitting the data. That is the interpretations, that it is not happening just by chance. Of course, there are other ways to reduce random fits to data, and size of hypothesis based on the data presentation. For example, minimum description length principle we can consider. We will discuss these things again when the context in a much more fuller context, we'll see them. Now the overfitting of this data also, we should look at it. Now some question. Okay, so you can see that it may not have the best generalization performance. As you can see, as I was mentioning, that just getting a consistent hypothesis is not going to serve your purpose, because maybe that consistent hypothesis is not really the target function. It is it is just satisfying some of the conditions of the target functions, of some of the conditions. It's a limited data on which you are looking at it. So there is certain overlapping region of this, your hypothesis with your target hypothesis, target function, hypothesis for target function. But the problem gets more complicated when there is a noise. So even if you have noise free also, then there was an issue. But if it is a noisy data, then you will have much more, this problem is severe. And then overfitting a noisy data, you will get, your effect would be very significant. That means you will get very low generalization accuracy, or I should say higher generalization error in that case. And already we defined what is meant by overfitting in this context, that suppose you have a hypothesis and H, and you have certain kind of generalization error. Suppose there is another hypothesis H prime, and also now you have hypothesis H which has a smaller training error with respect to another hypothesis H prime. But now if you consider the general test data, then you will find that the H prime has a lower error, generalization error, than H. Now that is the case of overfitting. That means H overfits the data, because there exists another hypothesis, though it has higher training error, it has lower generalization error. So just a figurative explanation that if you consider also the tree as your every tree instance as your hypothesis, and complexity of tree is defined by the size of the tree. Now there is a certain size at which you may get a maximum testing error, though your training error is going to be reduced. It is going on getting reduced as you increase the complexity, because you are trying to fit as many as examples possible by increasing the depth of the tree, and by which you are going to reduce the training error. And finally, when you reach a consistent hypothesis, your training error can be set to 0. It is possible also, that we have discussed. But the testing error, you will find more and more it is getting higher in those situations, because it is the overfitting of the data that is taking place. I think I will skip this particular diagram. We discussed this part. So this is also I will be skipping, because this example I discussed in the previous class. I will be quickly going through some of the topics which we discussed here. So we mentioned about two basic approaches. One is pre-pruning approach, another is post-pruning approach. And as you see that in pre-pruning approach, you are taking a decision at that point itself, at every point, whether you should grow further or not. So using some criteria, you are always taking a decision for that. Whereas post-pruning is that you form a consistent hypothesis. That means you form the full tree by making the training error 0, and then look at the decision nodes, that whether some of these nodes could be removed, and still you are getting whether by removing that node you are avoiding overfitting, which means by removing that node you get an alternative hypothesis, and now you see you understand that its training error is larger, because that's why you have grown the tree from that node. But you see that what is the test error. So you can use your validation data set, you can use your usually validation data set that is being used there. And if you find that your test error is lower, then you may go for pruning that particular node. So there are different methods for evaluating subtrees to prune. You can have cross-validation, you can have statistical testing, you can have minimum description length. And whereas in cross-validation, we discussed this part also, that there are different ways you can do cross-validation. Like you can divide the data set as a training set and validation set, and you can take different instances of that. That means you can have different partitions, and finally you can find out what is the average test error out of that. So that is the kind of cross-validation, but there are other methods also. Then there are statistical tests which I will be discussing in subsequent topics. So by which you can evaluate two hypotheses and statistically. The advantage of statistical test is that it is more robust, and you have a very sound theory behind the rejection of one of the hypotheses, or rather selection of one of the choosing one of them. Minimum description length is very interesting. What it is considered here, you consider what is the size of encoding of a hypothesis. So if I consider the size of the tree, suppose there is some way you can represent an encoding of a tree. So there is some different methods of encoding of tree. You can apply them, and you can consider its size. And suppose some of the exceptions for which you are growing the tree. Now you consider size of storing those exceptions. So that's also another encoding scheme. Now these two encoding scheme needs to be equivalent, needs to be normalized. Now you find out that what is the additional complexity. That means if the encoded tree with full size, with your full, I should say full tree, for example, that encoding, and when you prune the node, the other encoded size, if you find that reduction is smaller than the size of size of the exceptions, storing the size of storage of the exceptions, then you can choose for that hypothesis. So this is the kind of criteria. So this is further elaboration that what are you going to do when you are using this cross-validation approach. I just mentioned it, but it is just elaborated that you can partition the training data into grow set and validation set. So grow set is actually now your training data, and validation set is your test set. Build a complete tree for the grow set, and until accuracy on validation set decreases, you do that for each non-leaf node in the tree, temporarily prune the tree below and replace it by majority vote, and test the accuracy on the validation set. So basically, you are performing pruning. So while performing pruning, you have to convert that node as a leaf node. Any intermediate node, if you are pruning the subtree below it, which means that intermediate node has to be converted to a leaf node. That is the meaning of pruning. So which means that it should have a class level. Now, which class level? So you consider the training examples which are being handled by the subtree, and you take the majority levels from those examples and use that level, assign that level to that tree. So that is what it says. And now this has become your hypothesis. The connection got broken. I hope it is okay. All of you can see?
Yes.
Yes, sir.
And also the slide?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
Okay, fine. So let me consider. If you find that you have an increase in the accuracy, and with the greatest increase in the accuracy on the validation set, so you may have different nodes. The problem is that it's a chicken and egg problem, because when you are pruning some node, you are taking the effect of other nodes are not pruned. Now you may have several such pruning options. So you have to prune that node which has the greatest increase in accuracy on the validation test. And then now you can iterate this process. So use this less data to construct the tree, and sometimes done at the rules level. So this rules level post pruning is also interesting. I mean, the details are given in that book, Mitchell's book. You can check that.
Yes, sir. Hello.
Yeah. Tell me.
Sir, so I have a doubt in the pruning part. So you said that means we will apply it to all non-leaf nodes and convert them to leaf nodes. So I couldn't understand that part. So and then take the majority. So what
You have not understood this part. Okay. So, what's your name?
Somnath.
Okay. Yeah, Somnath. So, you have not understood that that first thing that no, you have to prune a non-leaf node.
How much?
That you have not understood. That
no,
you have understood.
Exactly happens means what do you gain if we?
No. First you tell me that no, you consider a non-leaf node for pruning. You are not considering a leaf node for pruning, no?
No. Yes.
So, because no, what is meant by pruning? Have you understood what is meant by pruning?
Yes.
What is it? Tell me.
So in this case of post pruning, it means that once we have a tree, then we again check.
That you are answering with respect to a very general meaning of a reduction of size. I don't want that. I want what is the task of pruning when you consider a particular node, the operation pruning. What do you mean by operation pruning? If you consider a node of a tree and we are saying that we are pruning the tree at that node, what does it mean? Have you understood that?
No, sir, not completely.
Yeah. So the idea is that if you choose a node, pruning means, say it is a tree structure. Now from that node, there is a subtree. So that tree is the root of a subtree. Sorry. That node is a root of a subtree in that tree. Every node is a root of some subtree other than the leaf node. Is it clear? Huh?
Yes.
Have you understood that?
Yes.
So pruning means that that subtree will be removed, but the root, that means that node will remain, but that new node will become a leaf node.
I understood that. So, but how we are gaining from that?
Have you understood this part? See,
yes.
Have you understood? So you tell me what you have understood then.
What is meant by pruning? So at a particular non-leaf node, we basically remove the subtree from that node and make it a leaf node.
Make it a leaf node. Now you have understood this part?
Yes.
Yeah. So now you say that when you make a leaf node, then what is the task you have to do?
We have to assign label to the leaf.
Assign a label. So how do you assign a label there?
By majority.
So have you understood?
So I am telling that. So the thing that
you
you
understood. First thing you have to by majority. Have you understood that?
Yes.
So what is that? Can you tell me once again?
So we remove a subtree from that node and make it a leaf node and assign label by majority vote.
Yeah, that's what it is. I told.
So I am asking is now the gain thing that you're gaining is the reduction in depth of the tree. So is
that you have not asked. See, that you have not asked. Initially, you told that this you have not understood. Now you have understood.
Yes, sir.
Okay, fine. So we are not bothering about that gain here. What we are looking at, when you have selected an attribute, we considered those information gain measure. But now we are considering the overall performance. We are considering the overall performance. So if you perform this operation, then you can perform once again the validation test, find out the accuracy.
Okay. Yes.
Have you understood now? So if you find any gain in that, then only you can go for this pruning. But no, question is that there could be several such pruning options. So which pruning you should get?
Okay. Yes, sir. Understood. Yes, sir.
Okay, fine. So that is what we discussed, and then now we are going for the other kind of strategies. So this is a strategy for pruning from the node level. But in fact, in a decision tree, as you know, you have actually a set of rules. Each path from root to leaf node, it defines a rule, right? So that we discussed. So a decision tree can be expressed as a set of rules. And what is the strategy? What is the principle that if any of this rule is satisfied for an instance, then we say that this example is a positive example in our context. I mean, what is the decision has been taken? If any of the rule is satisfied, no, I should not say positive. Basically, what we are finding out that yeah, that's what, right. We are only considering those rules with respect to positive, negative, which are only capturing the positive examples. And then for two rules, otherwise, no, you have to consider multi-class also, you have applied those rules. But finally, if one of these rule gives you the label and you are expecting that level should be the output, that is what you are doing. And accordingly, you can, and using that, you can perform the, you can measure the accuracy, etc. So what you can do that check each of these rules, structure of this rule. So what is the structure of a rule? I will give you an example. Say this is the structure of a rule. Say if outlook equals sunny and humidity equals high, then the play tennis is no. Actually, the full tree has not been shown here. After high, the level was no. Right? It is actually negative example. So you have all possible rules. Now the question is that this rule could be modified. How it could be modified? You can, for example, we consider these two things: outlook equals sunny and humidity equal high. Those are the clauses. Okay, those are the conditions. So these preconditions can be pruned. One of them could be retained because these are all in conjunctive form. So one or a few of them could be written. So what you can consider, you consider all possible type of rules that could be derived from this by modifying the preconditions in that conjunctive form. The simplest way is that no, you consider one of them is no removed, and then you apply the rule set with this modified rule. You apply the whole rule set and find out what is the performance. And if there is any gain in the performance, then you can go for pruning of that particular preconditions. But now actually you are working with not exactly in tree structure, but with the rule sets. The advantage here is that you have the flexibility of pruning different kind of preconditions, which was not possible in the node level pruning. It's more rigid. Either you retain or you prune the whole subtree. But here, from the path also, you have some more variations. So there are various extensions are possible from this basic algorithm. Like you can handle continuous valued attributes. In fact, yesterday some of you have asked me these questions. Today I will give you a brief overview of that how continuous variables are handled. Also attributes with many values, which is a kind of, I should say, similar to the problem with continuous valued attributes. Then there could be training examples with missing data, which means you may not have training examples of having certain attribute values. Some of the attribute values, though your attribute, in the domain of the attribute space, there are many values, and training examples, that value has never appeared. But no, you cannot ensure that in your instance it will happen. So if you get an instance with certain missing value of your training examples, how are you going to handle? So that means in your decision tree, you have to consider those also. And there could be other factors with attributes, like we have only considered the information gain, but some of the conditions for attributes, in real life, there would be certain costs of checking those conditions for those attributes. So if I want to implement something in practice, maybe some attributes checking will be preferred because they are less costly. For example, in the diagnostic test, already we encountered this fact. The physicians, they try to avoid to suggest the expensive test in the beginning. though that might have a better decision process. But there are other issues, not only cost on expenses, but also cost on side effects and other things. So that's why if we consider those other factors in the tree learning algorithm, you need to modify this particular attribute, choice of attributes, the rules for choosing attributes. So you need to use other impurity measures. And also there are another kind of decision tree in your assignment also. You have this regression tree. In the last yesterday also in the doubt clearing session, somebody asked about this. This question was, so we will also consider how to handle that in a brief way. So in the continuous valued attributes, what we can do, that we can create a set of discrete attributes from continuous variables. So it's a kind of discretization. Usually it's a continuous variable, means it's a real axis. You consider a real axis for representing the domain of that attribute space. And then intervals of real axis could be considered as some of the discrete discrete values for those attributes. They could represent those discrete levels. And intervals, I'm saying that non-overlapping intervals. They could say you consider this example that temperature is given by these values, where the value could be from a very large range, and it's a kind of a continuous variable. So and there are decisions also. Now, which value, how to handle this? So as you understand that we may consider that certain critical value, and so less than that value we may consider one kind of conditions for the attribute, and higher than that value would be considering other conditions. So we are converting some kind of categorical representation of a continuous variable in that manner. Say lower value means say low temperature category, higher value means high temperature category, and number of categories can also differ. It may not be always 2, but a simple case is like that. And there are certain rules by which you can define. So there are many possibilities, of course, and you have to consider so which candidate is more suitable. So in this case, just by heuristics, you can see that we have chosen a particular threshold, and where the levels are also changing. So if you represent temperature in a monotonic sequence from the training examples, and you will see how the level distribution of the levels, they vary over that sequence. Now, if you observe the transitions, usually those are your point of interest. Those are the candidates. It has been proved also theoretically that those transition zones are there is certain criteria based on which those transition zones are favored. So in this case, what are the transitions you can see? You can see between 48 and 60, and again at 80 and 90. So these are the two candidates. So which are you are going to choose? I think I have a better slide. So one of the policy could be that you can choose it by information gain function, which means the same strategy. Only the strategy here is that now we have, if you are considering this temperature as an attribute, in the information gain should be the maximum of the candidate threshold. So threshold conditions. That means you consider one candidate threshold, that's say 48 plus 60 by 2, and then you use that to measure the information gain with respect to temperature, then as a two-valued attribute. That means low and high with respect to that threshold. And then you find out what is the information gain. And then another situation, you consider 80 plus 90 by 2. That is the threshold. And then with respect to that threshold, once again, you find out what is your information gain. And compare these two. The maximum information gain where you are getting, you choose that threshold. as a possible considerations, and then use it in the comparisons with all other attributes further. So this is the kind of policy. You can have more than, of course, one threshold. I just discussed with respect to a simple case, but you can have more than one threshold. Typically, where target values change quickly. Quickly means there is a transition. There is a transition. So attributes with many, and the second other problem is that you can have attributes with many values. Here the problem is that the problem is that now if you have an attribute which has many values, then usually those attributes are selected, because you know that the entropy of that attribute is going to be higher. So any kind of ordering with respect to that attribute will lower the entropy. Will have a higher. Will have a better lowering of that entropy. So that's why gain will be higher. Say the birth date attributes, where you have 365 entropies, and if I assume that if you have a very large value, as you see that your ni by n is is going to be 0, and so you are having this. So in this case, your gain is approaches of maximum value. In this case, this is a bit confusing. The idea is that if you have a very large number of values, as you can see, the highest entropy, if you assume all of them are uniform, highest entropy would be the number of levels, which would be log 2n. And if you are going to put some order, then you are going to have the lower gain. So in that case, we use a strategy called gain ratio. Maybe today I will stop here and I will start. I will again take this issue tomorrow to discuss, to elaborate further.